Dear Professor Cockell, thank you very much for joining us today.
Thank you. No, it's a pleasure to talk to you.
Before we start with the actual conversation about concrete things, so to speak, there's something that I would like to ask you in regards to your background. When I look back on my childhood, and I remember, of course, I believe that every child has an interest in some way or another about the space, about life in general. I remember reading a book, I cannot remember which. I cannot remember neither the author nor the name of the book, but it was about extraterrestrial life, everything from like the alleged abductions and so on and so forth, down to the really concrete things such as the Drake equation, which, if I can recall correctly, of course, is like I'm calculating the possible number of civilizations in the galaxy and in the galaxies in of themselves.
Yes.
I remember that was the thing that motivated me, to be a little bit, so to speak, interested about space and things in general. What has been the thing, if you can recall, that might have motivated you to take the path of, studying about life and in the end, taking the path of astrobiology?
When I was 6, I went to a boarding school. So we had a library in that school, and I often used to go there and read. And, English boarding schools at the time I went were quite conservative places. And alien planets were an escape from those environments. And when I was about 7.5, I was sitting in our school library reading a book about the Apollo program to the moon and the way in which the astronauts had landed on the moon and some of the technicalities of that interested me less. What enthused me was the part at the end of the book where there is a discussion about building settlements on Mars in the late 1980s. And I was absolutely convinced that, by the 1980s, I would be going to Mars and traveling to that planet and being part of a human settlement effort. Unfortunately, that hasn't happened. In fact, intriguingly, every 10 years of my life, the exploration of Mars seems to be 10 years into the future. So one hopes that maybe with commercial spaceflight that will change, but that's really another matter. But in answer to your question, it was that thought about standing on another planet that absolutely gripped me. And I was also at that age very interested in polar exploration. I'd read about the exploits of Shackleton and Scott. And in that sort of moment, I think, of being in the library or over that period of time, there came to me a sort of connection between the adventures of Scott and Shackleton that intrigued me so much with the idea of going and exploring other planets, traveling to Mars. And the connection of those two things just enthralled me. The idea that you could go to Mars and stand at its polar ice caps or climb its mountains, and that there were these great frontiers that were open to humanity and our civilization that no one had ever been to, but we could go to these places and explore. So I think it was that really made me enthusiastic for space exploration, and has ever since then been a very strong motivator in my thoughts about what I want to do. I'm very much motivated by this idea of the human exploration of space.
But what might be the biggest goal within that, human exploration of space that you can think of? Something that has perhaps been the biggest motivator for you, because the space exploration as a topic in and of itself is a really broad one.
Yeah, I think the Viking Lander was a strong point of a real a point where there was a real mission, where there were real images being sent back. And I do remember running downstairs in 1976 when I was still at this boarding school where I was reading about the human exploration of space. And we used to have a newspaper that was sort of laid out on a table where you could read about the news. I remember running down and seeing on the front page the first images sent back from the surface of Mars. And that was, I think, a very concrete moment where you could actually see what it would be like to stand on another planetary surface and look out. It may have been a rather dusty, boring desert plain, but it was a Martian desert plain. And it was very difficult to look at that image and not be inspired by this idea that there were these other worlds that were strangely Earth-like. I mean, as I say, Mars is very alien to the Earth in many ways, but in many ways it's a very similar planet as well. It's it has volcanic rocks, it has deserts. And when you look at those images, you're reminded of images of extreme places on the Earth. And I think for anyone who has that spirit of exploration and an interest in seeing humanity explore, always seeing images of the surface of other planets invokes some very strong sense of, firstly, I want to go there, but secondly, there's somewhat sort of mysterious influence it has over your thinking, the sense of imagination that one could stand there. Someone could be standing there in the future and one could make some contribution to making that happen. That's a very enthralling and exciting thought, particularly when you're 8 years old.
Yeah, but I mean, it also is kind of mind-boggling, because once you start thinking about it and once you start thinking about the things that need to go right, it really takes both your this is something that I like, that I'm sort of guessing. It creates a sort of a mixture between optimism and pessimism. Pessimism because of all of the things that need to be done, but optimism because it's quite like they're viable. They can be done.
Yes, I suppose it depends upon how you look at the things that need to be done. You can certainly be pessimistic, but even buried in that is an optimism about the things that we have to do, the potential that we have as a species to solve some of our greatest challenges, whether that's living sustainably on the Earth, dealing with nuclear weapons, dealing with a pandemic, as the case may be. All these things represent challenges, but they also represent opportunities for us to show the best in ourselves, to face up to these challenges. And through those challenges, through those problems, then emerge these greater opportunities, such as to establish a permanent human presence beyond the Earth, to build a spacefaring civilization. As you rightly say, there are many steps to achieving those goals, but I think that we have the capacity to do that. We have the intelligence to be able to work out how to do it. And in some sense, the difficulties that we face both on Earth and in moving out into space are part of the thrill of existing. And in fact, more specifically of being a scientist, I think, is embedding oneself in a very both intellectually, but in a very in a very real way, and doing experiments to try and contribute towards that future.
Yeah, but I mean, it's not only through experiments. There's a lot of different methods that one can actually contribute towards this. And one of the things that you've sent me via email actually has been about a program with Scottish prisoners in terms of going about planning the stations on Mars and the Moon. I mean, how did that program come to be, and what are the goals?
Yeah, so it's always occurred to me that prisons are a little like lunar and Mars stations. You've got a confined population that can't go outside very easily. The population itself is run in quite a hierarchical way, in quite an organized way, because a prison needs to be well organized. But at the same time, there are these very informal groups within a prison, and there's a lot of interdependence between the people living there. So it's always occurred to me that prisons are a little like stations. And one afternoon, I really quite literally Googled who the head of learning was and education in Scottish prisons. And I emailed that individual, and I said, I've got this idea, can I come and talk to you about it? And I went to the Scottish Prison Service, and I proposed a program to try and get prisoners to use their experience of living in prisons to think about how we could successfully explore and settle the Moon and Mars. And they said, well, why don't you come and give some lectures in some of our prisons, and we'll see what the prisoners think. So I put together a short program where I went around 4 prisons in Scotland and gave them lectures on space exploration, astrobiology, and then we had a short activity for an hour to design a Mars station just to see whether they would be interested. And they took to it with great enthusiasm. And that resulted in a full course that I developed that's run in prisons over several weeks, where the prisoners go through the steps of thinking about the challenges of living on the Moon and Mars, designing a Mars station. They do creative writing competitions where they write their first email home from Mars. We've even had prisoners write Martian blues music, so they can do music as well. They have to come up with a sort of memento of Mars exploration. That could be a poster to try and entice tourists to come to Mars. It could be a diary of an expedition. It could be a diagram of an expedition vehicle. It could be anything. And then in the last part of the course, we get them to think about governance on Mars. What makes a good citizen on Mars? How do you behave towards your fellow citizens to create a successful society on Mars? And in some sense, that exercise is an exercise in thinking about what makes a good citizen on the Earth. We want someone who can, challenge the laws through democratic processes, but will not commit crime or do very destructive things towards other human beings. So how do we have a population where there's healthy dissent, whether that's dissent against the government or against their local society, but at the same time have an ordered society where people can live peacefully? And a very good way to think about that is actually to go to the Moon and Mars and to consider an artificial new society and how you would build a society successfully. So that's the final part of the course. And the result of that course has been that they've published books. We've formed a collaboration with the British Interplanetary Society, and they've now written 2 books, Life Beyond, From Prison to the Moon, and Life Beyond, From Prison to Mars, which is a collection of all of their designs and their art and their technical drawings and their scientific drawings. So it's been enormously successful, and we've just completed in the last 2 weeks transferring the course materials into packs that can be done by prisoners in their own cells. So what we've tried to do is create a course where we don't have to physically go into the prisons and educate the prisoners. They can work through this material from beginning to the end, and then they can send in their contributions to the Prisoners Education Trust, which is a charity that works with education in prisons that we formed a partnership with here in Edinburgh with this charity. And they will receive all this material, and then we will publish more books and put it online. And that material will be available in the next month, and it can be done by any prisoner anywhere in the world. So they'll be able to download it, and they'll be able to work their way through and come up with designs for stations. We're also launching a lunar and Martian cookbook developed by prisoners. So one of the activities is to draw your favorite food or come up with a recipe or describe what the banquet might be like on Mars or the Moon. And we're going to put all that together, and we're going to come up with the prisoners' lunar and Martian cookbook, which will be developed over the next 2 years or so. And that will be a very innovative output from prisons. So what are we trying to do here? We're trying to, so there's 2 ways in which you can educate prisoners. Either you can go into a prison and just offer educational materials. You can lecture them, you can give them interesting things to read, which is a very conventional approach to education. It's just like you would do in any school or university. Or you can ask yourself, which is really what I was trying to do here, what is it about the prison environment that's unique? Are there aspects of the prison environment that prisoners know about that the rest of us don't know, that would give them an opportunity to learn the excitement of doing original research, coming up with original ideas? And like I said earlier, prisons are a bit like planetary stations. So in some sense, prisoners have an experience of living on the Moon and Mars that the rest of us don't have. So through this program, they're learning to take pride in something that they have a unique experience of. And by writing books, they are learning that they can make an original contribution to society that is very new and presents ideas that have not been presented before. And then they leave this course having contributed in a completely new way to one of civilization's most ambitious goals, which is to explore and settle space. And that's enormously rewarding for them, because they learn that education is fun, that within a few weeks you can go from no knowledge to publishing a book. And that's quite a revelation for many prisoners. And above all, we get people who have maybe had some difficult times and have ended up in prison to contribute to one of society's, as I say, most ambitious ideas, which is to settle other planets. And that's a big step for someone who maybe has had a very negative view of education beforehand. So what we're trying to do is to get prisoners to really contribute to advancing society beyond the Earth. That's exciting for us, and it's exciting for them as well. And we've been surprised, I would say, not surprised, because they have a lot to offer, and some of them are very bright, but surprised at the level at which we've had success in implementing this project and the enthusiasm with which they've picked up this Life Beyond project. So this has been enormously rewarding for me to do in the last sort of 4 years.
So, I mean, that's a really, really good thing in terms of, benefiting the prisoners and showing them, as you've actually emphasized beforehand, that, I mean, this is, I believe, something that can be used generally in life. No matter the situation that you're in, there's always something useful that you can get out of it, but not just for yourself, but for the society too. And this is, well, I mean, I haven't thought about, the prisons being sort of like moon or Mars stations, like space stations in and of themselves. But it really is like you have to be self-sustainable. You have to learn how to communicate with people who are in some ways really different from you, but are also really self-sustainable in and of themselves. And a lot of things depend on the in simple terms, on the dialogue between the people. Of course, there is like a governing body that's keeping the order, but a lot of order depends on the people themselves. And so looking at that concept of order and actually establishing a functional civilization outside of Earth, actually, what might have been the things that you have actually learned through that program? What have been some of the insights? And perhaps not only through this program with the Scottish prisoners, but also via other programs in terms of understanding the components necessary for sustaining a civilization outside of it.
This is a very interesting question. The scientific question of how you sustain a civilization is interesting, but it's more of a technical matter of producing oxygen and food and water. And these are things that can be addressed by scientists and engineers. But this question of how you build a society, I think, is a particularly interesting one. And over the last few years, in fact, starting about 10 years ago, I actually wrote papers and several books with colleagues on extraterrestrial liberty and organized 3 workshops in London on extraterrestrial liberty. And the question that underpins this, which is not a new question, but it takes on a new force, I think, in the extraterrestrial environment, is how can you have a free society in an environment that's instantaneously lethal? So here on the Earth, if you don't like your government, you can at least run off into a forest and maybe forage for some food or get some water in a river and plan a revolution. That's a rather extreme situation, and one hopes that maybe you can challenge your government in other ways rather than having to form revolution. But of course, revolution has happened in the past and sometimes may be necessary. But at least you're not going to be, it's difficult for the government to kill you within a matter of seconds. But of course, if the government controls your oxygen, the air you breathe on a second-to-second time scale, then it has the capacity for total control over your life on a second-to-second time scale. And this, in my view, is one of the central problems of the extraterrestrial environment. You construct a society in a place where not even the oxygen you breathe can be obtained except.
We seem to have minor interferences. Professor Cockell, I'm not sure if you can hear me, but you froze. Yeah, so we don't have to start all over from the beginning. So just for the viewers to know, we have had some sort of a problem with the internet on my behalf. So it's dropped off, but don't worry, we're starting all over again. So we've been talking about actually the oxygen, in terms of providing oxygen for the space stations, of course, outside of Earth, not being democratically supplied by the government, and whether or not it's possible actually to sustain a democratic government outside of Earth, precisely because a lot of things will depend on the government itself.
That's exactly right. I think the problem in space, and it's no different on the Earth, I mean, this is a challenge that human beings have grappled with for a long time, I mean, millennia, but is the question of how you disperse human power to ensure that people are not tyrannically under the control of an authority that wields this power and sometimes abusively over a population. And in space, where an authority is controlling the very oxygen you breathe, the problem becomes particularly acute. So as I say, it's not a new problem, but it's accentuated in the space environment. And the sort of solutions that you might consider for this in space are, I think, similar solutions that you have on the Earth, but just in a slightly different way. For example, you could maximize the number of oxygen producing machines. So let me give you an example. On Mars, it's possible to make oxygen by breaking up the carbon dioxide gas in the atmosphere and releasing oxygen from that gas. And in that case, you've got oxygen produced directly from the atmosphere. And you can imagine individuals on Mars owning their own oxygen producing machine. In fact, this machine is going to be tested on the Mars 2020 rover that's going to land on Mars hopefully next year, the NASA rover. They're going to test this technology for making oxygen from carbon dioxide. So there's a machine that an individual could own that you could put in your habitat, and it would extract carbon dioxide from the atmosphere and make oxygen. Another type of way of making oxygen is to dig up water from the ground and break up that water and electrolyze it to produce oxygen. But of course, that depends upon digging up frozen ice, and that might be under the control of an ice company that
Yes.
might be controlled by the authorities. And then the ice has got to be brought to a facility to melt it and to electrolyze it, and that plant that melts the ice and electrolyzes it might also be under the control of some corrupt official that's being controlled by the government. So these are the sorts of examples I suggest of a technological approach to some of the problems of freedom in space. If you go for the technology where everyone can own their own oxygen producing machine, you remove those intermediate steps between the authorities and individuals. And this is no different on the Earth to trying to disperse power, trying to increase competition, trying to ensure that people are not under the control of ministries or corporations that are run by single corrupt individuals. We have the same problem on the Earth, but the problem will be particularly acute in space. So I've spent several years thinking about this, and I'm actually right now editing a book entitled The Institutions of Extraterrestrial Liberty.
Nice.
With 20 or 30 co-authors who are going to be writing.
I will have to read that one, just to tell you right off the bat.
It will be published at the end of next year, or submitted for publication at the end of next year. So it will be out in 2022. And that's a wide variety of people I've brought together to address this question of liberty in space. How do you build free societies? What are the challenges to constructing societies where people at least have some sense of independence in these very extreme, instantaneously lethal. I think, like on the Earth, it will be an ongoing challenge, and people will have to continuously discuss how do we build societies where we can experience some semblance of freedom. Of course, not forgetting that we want some collectivism in these societies as well. You don't want a habitat on Mars full of a group of anarchic individuals who run around smashing up the habitat and causing depressurization. You want some sort of organization and order. So it's this balance, right, between the amount of collectivism and the amount of individualism. This has always been a conflict in the way in which human societies operate, whether it's ancient Athens facing up against military Sparta, or whether it's the West facing up against the more, I would say, the more collectivist society of the Soviet Union. For thousands of years, there's always been this balance about which is a better society, and how much collectivism and how much individualism do you allow to achieve the goals that you want as a civilization. This question will follow us out into space, and we're going to have to find solutions for it. So it's a fascinating question because it's taking something very old and applying it to a completely new frontier, if you like. So I'm really taken by this question.
But it's also a thing that, as you emphasized numerous times throughout your explanation, it's not just a matter of, who governs what, it's a matter of how do we actually provide for the necessary material for the life outside of Earth. For example, of course, if we would have, if the human civilization were to have these like oxygen producing masks, that's all good. But then the question comes, how do we actually, so to speak, establish a worthwhile and a quality partnership with a company that is actually able to provide for that? And I mean, not only the things such as oxygen, but also the things like, one of the questions that comes to mind is, how do we actually build a station? Do we drive all of the material towards Mars or the moon in and of itself, or do we extract the certain material from the moon or Mars or other, actually, such as I would actually like us to talk about the asteroids themselves?
Yes. I think there's a there's a process that will occur there in terms of a greater independence from the Earth. And clearly, to begin with, you will take material with you. You will travel to the Moon and Mars, asteroids. You will take food with you. You will take certain building materials. But the idea is that longer term, you increasingly begin to extract local minerals and resources and become self-sufficient. And in fact, just to discuss another project, on Sunday this last week, we launched an experiment to the International Space Station, my group, called BioAsteroid, which is right now up on Space Station and will be activated in the coming week or so, looking at using microorganisms to extract elements from rocks. And last year we sent a similar experiment to Space Station called BioRock, where we demonstrated for the first time the extraction of elements from rocks using microbes in space, in that case rare earth elements. So the idea is that eventually you don't want the mass and energy cost of shipping materials constantly to other planetary bodies. The problem with that, of course, is it then depends upon people making those shipments. If a government decides it's not interested in Mars exploration, then suddenly your Mars settlement falls apart because there's no longer resources. So if you really want to establish a permanent foothold in space, it is essential that at some point you create a self-sustaining settlement that can operate independently of the vagaries and changes of political circumstances on the Earth. And that requires you to make a switch to extracting resources, whether that's using microorganisms or physical and chemical methods, to get metals, to produce oxygen, to produce food, pharmaceuticals, whatever else it is you need in the extraterrestrial environment. And I have the very great pleasure of being on the Science Advisory Committee at the moment of a NASA center called the Center for the Utilization of Biological Engineering in Space, CUBES, which is looking at exactly this process of how we can use biology, microbes and plants to do things for us in space. So here on the Earth, of course, microbes make yogurt. They help us to make soils. They also do bad things like cause disease, but microbes do a lot of good things for our society. And what we really want to do is employ them as our allies in building a settlement beyond the Earth, whether that's making us something as basic as yogurt to creating new types of microbes that can make plastics and mine elements. So I think you're absolutely right. We have to go for a transition from the initial settlement where a lot of the material comes from Earth to something that can sustain itself.
And in terms of the BioAsteroid actual mission, in terms of using the microbes in order to figure out whether or not and which material is possible to extract from beneath the crust of the asteroids, how does a microbe actually do that? What's the, so to speak, like the biological process behind it?
Yeah, microbes have been mining, if you like, rocks for billions of years. They have, and the reason why they do that is because within rocks are nutrients that life needs. For example, life needs nitrogen, it needs phosphorus, it needs sulfur, and these elements are within rocks. So microbes, for example, secrete acids that can break down the rock and release these elements. They can also change the chemistry around a rock. Even if they're not extracting nutrients from the rock, simply by growing, they can change the chemistry around them. And that causes the pH or the chemical environment around the rock to alter. And as a result, the rock might leach particular elements. And so human beings have employed this in the process of biomining, which is mining rocks using microbes. And about 25% of the world's copper is today extracted from rocks using microorganisms. So this is not a theoretical process. It's a hugely important commercial process even today. And essentially what we're doing is we're tapping into this, this 3.5 billion year capacity that the microbial world has had to eat rocks, and we're employing it for industrial ends. And just going back to the former comments that I was making, we can do the same things in space as well, because other planets are just made up of rocks. The Moon or Mars, these look very exotic places, but they're just made up of basalt, volcanic rock, like many areas of the Earth. So when you start thinking about processing the Moon and Mars to build settlements there, many of these processes we already know how to do. We do them on the Earth on a daily basis. We're just taking them to another planet, an exotic location, but the process is the same.
But I mean, it doesn't have to be necessarily a planet. As far as I've actually understood, one of the most probable places to find alien life, of course, not alien in terms of like the of intelligent civilizations, but in terms of just finding life outside of Earth, are the moons, actually. So, for example, Titan, Europa, especially.
Yes.
So, like, as Titan is engulfed in ice, if I can remember correctly, or was it Europa?
It's Europa, yeah. Europa, which is a moon of Jupiter, and then Enceladus, which is a moon of Saturn. And Titan is also a moon of Saturn, but it has a very thick atmosphere. It's very cold on the surface. It's 94 Kelvin, so it's minus 180 or so. It's a very, very cold environment. So it is covered in ice.
Yeah.
It's covered in solid water ice, but not quite in the same way as the ice you can see directly on the surface of Europa and Enceladus. All these places are very cold. But what's exciting about these moons is that because of tidal interactions with other moons and the giant gas planets around which they orbit, the ice within the interior of these moons has been melted. And so we have evidence for oceans beneath the surface of these moons. And in the case of Enceladus, not just circumstantial evidence, but really direct evidence of plumes erupting from the South Pole. You can actually see the oceans erupting into space, the ocean erupting into space. So these are good places to test the idea of life elsewhere, because of course there's liquid water, which is one of the requirements for life. And we know that these oceans have many of the other elements required by life to grow and replicate. So in some sense, you could say that all we have to do is fly to these moons and grab a sample and bring it back to the Earth, and we can finally answer this question of, is there life beyond the Earth? It may not be quite that simple, but certainly these are very good targets to address this question of life beyond the Earth.
And what do you believe are the probabilities that there is actual life on these moons?
You know, I always disappoint people because I'm a professor of astrobiology, and people seem to think that I have some insight into this answer, and or at least I should give some learned, rationally thought out answer. And I always have to look at people and say, well, I have absolutely no idea, and I've no idea any more than you. And let me explain what I mean by that. At the moment, we don't understand what the processes are for the origin of life. We have some good ideas. We know, for example, that the amino acids that make up our proteins are found in meteorites. And then we know that lipids that make up our cells are found in meteorites. We've never found whole proteins, and we've never found whole cells, but we're beginning to get some idea about where the building blocks for life come from. And the fact that we can find them in space suggests that they are common throughout the universe. But we don't know how those building blocks turned into a replicating, evolving life form. And here's the problem. Within that scheme of chemical reactions, if there was one reaction in there that was extremely unlikely, then it could be that life elsewhere is extremely unlikely. So how many stars are there in the known universe? Well, something like 10 to the power of 22, plus or minus a few orders of magnitude. We don't know exactly. But let's just say there was one reaction in that origin of life sequence that had a probability of occurring of 1 in 10 to the 30. Then it could be realistic that we are the only life in the known universe. And no matter how many other stars there are in the rest of the universe, it's still statistically so unlikely that we are the only type of life. So this brings me back to my rather feeble answer to your question, which is there is no scientist on this planet that can tell you whether there is a high probability of finding life elsewhere. And there is no scientist who can tell you we will find life in this amount of time. There are people that claim this. You'll often see very famous people say, I predict we're going to find alien life in the next 30 years. But they're just not doing very good science, or they're just having a light-hearted speculation, which is fine. I mean, one shouldn't get too serious about this. People are entitled to speculate, and that's all good fun. But the scientific reality is that no one can give you an answer to that question. But what is thrilling about astrobiology and planetary sciences and astronomy at the moment is we're now building missions, and we're now discovering planetary bodies, like you said earlier, the icy moons that have these oceans. We're discovering places where we can go and test this idea of life elsewhere. We're discovering places that seem to have the raw materials for life. And now we can go there and look for life. We're building telescopes that will allow us to look at the atmospheres of exoplanets, planets orbiting distant stars. And we'll be able to look in those atmospheres and see whether there's gases associated with biology, like oxygen. So what is exciting is, although we don't know the answer to this question, for the first time in a very long time, we now have the scientific and technological ability to finally go out there and get some sort of answer, even if that's a negative answer, to get some sort of answer as to whether there has been, or whether there is life in our own solar system, or maybe in planets orbiting distant stars. And that is a very different position than where we've been for the last few hundred years, which is very much stuck with interesting but nevertheless scientifically unconstrained speculation about alien life. So I think my general comment to you would be that we're getting nearer to answering this question, but we still don't have an answer. And even a professor of astrobiology can't give you any rigorous answer to this question of is there life elsewhere, or when or if at all we will find this other life.
Yeah, but as you said, actually, it doesn't just come down to the knowledge of space, like, so to speak, per se, in and of itself. It comes down to understanding how did the origin of life actually occur on Earth. And that's one of the things that I've understood, like when one talks about astrobiology or mentions, one predominantly probably believes that, it concerns only this, like thinking about and doing research in like layman terms, about the possible life or life in space, whereas it actually concerns about the life on Earth itself. And it's really apparent why that is so, because if we don't understand life on Earth, how are we supposed to understand life outside of Earth? And okay, so maybe to like further investigate this thread of thought, okay, so we do not understand completely how the origin of life had actually occurred here. But what might be actually some of the elements that that attribute to the creation of life, perhaps like things such as like the carbon-based materials, like water? What are some of the elements that are necessary for life to occur?
Yeah, you raise a very good point, which is that the Earth is just one planet. It's n=1, and any scientist doing any experiment with one sample should be concerned. But that's all we have at the moment. We have our one planet, n=1. It's unfortunate, but that's the material we have, and we have to try and construct ideas about life across the whole known universe based on this one example, and that's a limitation one has to deal with. Nevertheless, we can get good ideas. As you rightly say, astrobiology is not just about search for alien life, although that tends to be the focus of the media. Astrobiology is very much about the origin of life on our own planet. In fact, biology as a field generally is about trying to understand life on this planet, how it originated, how it's evolved, why it is like it is. And I think one of the fascinating questions that you have raised is, is life on Earth a template for life elsewhere? Can we learn universal things about life on our planet that would guide us in the search for life on Earth, or just tell us about life as a phenomenon? And is that a plausible thing to do? And I think the answer is yes. Even though we've got the n=1 problem, we've got our one sample problem, the periodic table is universal. We know that other galaxies are made of the same elements as life on Earth, because we can observe distant galaxies and we see sodium and hydrogen and helium. There's not some strange set of elements that don't fit on our periodic table. The periodic table is universal, and it's quite limited. And you can look at those elements and you can study their chemistry, and you can learn things about the way they behave. And then you can look at life and you can say, why does life use these particular elements? Why does it use carbon instead of silicon? And you can actually work out why that's the case. You can realize that when you have silicon, for example, and you add it to oxygen, which is a very common element in the universe, it forms silicon-oxygen bonds. And those silicon-oxygen bonds form these long chains that you and I are all familiar with as rocks and minerals. So silicates are silicon chemistry. So silicon tends to form these very inert compounds. And then you ask, well, okay, but surely life has tried to make a silicon-based life form instead of a carbon-based life form. And if you go out into the natural world and you ask yourself, what has life done with silicon? And you look in a sponge, for example, you will find spicules, which are these little structural materials that sponges use to hold themselves up. And plants produce these structures called phytoliths, which are, again, silicate materials made from silicate materials, a bit like rocks. And phytoliths are used by plants to grow up against gravity. So they're essentially structural materials included within the plant structure. So in other words, biology has done rock-like things with silicon. And why is that the case? Well, because silicon likes to bind to oxygen and produce rocks. And so there are reasons for the way in which life uses elements that are not idiosyncratic events in the evolution of life on Earth, but are actually tied to the universal principles of the periodic table that themselves are tied to the way in which electrons behave. Actually, the Pauli exclusion principle is the basis of the way in which electrons behave in atoms and the way in which atoms interact to do chemistry. In other words, we see a universality in the reasons for the way in which life uses elements. And of course, life uses elements in different ways. In some organisms, there's more copper than molybdenum, and elements are certainly used in different ways by different life forms. But the fundamental structure of life is determined by the behavior of elements, and those behaviors are completely predictable based on fundamental physics. So I think that if you went to other planets, you would see life made of atoms, and you would see it using atoms in the same sort of way. So at the basic core material of life, you can make predictions. Of course, you couldn't go to another planet and predict that you would see Labradors on a distant alien world. I would not predict the existence of dogs on other planets, because of course, once you get to that large scale, you can have all sorts of weird and wonderful architectures of biology, whether it's extinct dinosaurs or, you know, centipedes that are 2 meters long that have been found in the rock record. Even in our own history of our own planet, we see an astonishing variety of organisms that are now extinct that are very different from the ones we see on the Earth today. So surely once you get to large organisms that are reflecting interactions with other organisms, with the gravity and the atmosphere of the planet, you can get a great deal of diversity. But I think that the n=1 problem is not so much of a problem as we tend to think. And there are principles of the construction of life that we are able to analyze along physical and chemical lines that we would also find to be the same with life anywhere in the universe. But it still remains a fascinating question. To what extent can we make those predictions, and at what level in the hierarchy of life can we make predictions about biology using physics and chemistry?
Yeah, it's like looking at it from the basic point of view, what you're basically saying, if I understand correctly, is on the basic level, if we were to find life outside of Earth, it would be pretty much the same as it is here. But as you go further on the hierarchy of evolution, for the lack of better terms, of, you know, multiple cell organisms having multiple cells, the similarities drop, but the fundamentals stay the same. And this is a really fascinating topic that you raised in your book. I've read it, The Equations of Life.
Yeah.
How physics actually governs life. And it's like one of the, it stays engraved inside my head, probably because of the cover, which is really, really good. I'll actually put it somewhere within the video so that people can actually see how the book looks like.
They did a nice job.
Yeah, it really looks nice. Like, it's not too complicated, but you can understand what the, like, as the saying goes here, like what the writer wanted to say with the cover itself. And it's basically like, okay, so I cannot remember. It's not the bumblebee. It's like a beetle. I can't remember the word in English.
There's a ladybird.
A ladybug, yes.
This is a little sort of red and black thing. Yeah.
So why, like, the question was like that you raised at the beginning of the book, like, why doesn't like a ladybug have wheels? Why did it have to actually develop these sort of legs? And why is this the thing with everything, so to speak, in life? Why didn't we develop wheels?
Yes.
It basically comes down to gravity and the terrain which we had to cross, for which the wheels wouldn't be applicable for.
I think that's really nice. And the comment you made about, you know, as you go up the hierarchy, things become less predictable. I think that's generally true. And I would agree with that point. The thing that may be slightly reticent about stating that as a fundamental sort of assertion of that book is the growing realization that even very complex organisms can be reduced to quite simple physical principles. So, for example, ants, you know, they look very complicated. When you look at an ant's nest, it looks like an astonishingly complex structure that must have been organized by some, brain at the center of it, the queen ant that thought this all up. And yet we now understand that it's built from simple rules between ants. So for example, if one ant starts building a hole, it will attract another ant, and those two ants will release pheromones that will attract more ants, and you get this feedback process where all the ants congregate in one area and build a hole. And then of course they get dispersed, or they get called off to other places, and the numbers drop, and that process ends. But there are all sorts of equations you can apply to these processes, and people have done a very successful job of applying quite simple physical equations to the behavior of ants, to the behavior of flocking birds, even to the movement of wildebeest over the landscape, and the way in which they organize themselves. Even at the level of populations of organisms, physics has something to say. And I wouldn't, again, I think there's room in there for remarkable diversity, but it's astonishing the way in which physics has made progress in describing everything from the atomic structure of life through to the behavior of a pack of wildebeest. And I think that would have been astonishing 40 or 50 years ago. And the book that I wrote, this book, Equations of Life, was really just to capture my own fascination and astonishment with this. And it did occur to me, which was, I think, the motivation for the book, that this was the case at the different levels of hierarchy of life. So I guess my attempted contribution in that book was to try and capture how that works at the different levels of hierarchy. But of course, physicists have been working in those different levels of hierarchy for some time. I was just trying to bring it together in a synthesis and say, isn't this astonishing, the way whatever level you look at, you can explain a lot about life using physics. It comes back to this question of, maybe despite the fact we only have one planet as an example of life, we might actually be able to learn a lot from this single experiment about life elsewhere. I think you summarized it very well. If you went to another planet, I would suspect it would look eerily familiar, life elsewhere.
What has been, there's a lot to learn, as you said. What has been the thing that excites you the most, or that has excited you the most, that you've learned through your research? What is maybe not even the thing that you've learned, but what is the question that intrigues you the most?
I have a problem with being excited about everything. and I constantly get distracted by things I shouldn't be doing that interest me, whether it's prison projects or whatever else. So my challenge in my life has always been to keep myself focused and sometimes pragmatically on where the grant money is coming from. But I would say that I think there's so many fascinating questions, and I think one of the thrilling things about being a human being, existing and having a consciousness is being able to actually take an interest in so many fascinating questions, whether it's how the universe is structured, how life came to be. Of course, my own true interest lies in biology. That's the thing I focused on. And I've always had an interest in space exploration from a very young age. So, from the days I started, really learning at school, I knew that biology and space sciences were the two things I wanted to do and to connect. I was privileged to do my postdoctoral position at NASA Ames at a time when astrobiology was emerging as a field, which really was the first time people tried to formally connect biology and planetary sciences in a way that might lead to jobs, basically, and to the possibility of doing this and being paid to do it. You can take an interest in linking biology and space, and lots of people did that before, but it was very difficult to do it in a way where you could turn it into a profession. So I was very lucky that happened. And so I think, if I was to answer your question, some of the most fascinating questions in science, at least for me, and that's certainly not shared by other people, but for me, the most fascinating questions are ones that do lie at this interface between life and what life is, biology, and this wider aspect of how life fits into its astronomical environment, how it came to be in a universe. I was sitting on the Isle of Taree in Scotland on holiday last summer, watching an otter, and it was walking along on the beach. And I was sitting on a bench watching this animal, and I just thought, how odd is that thing? Yeah. This is this lump of atoms that's made this carbon and phosphorus atoms, and it's sprung legs, and this lump of matter is walking around with legs on it, and it's almost horrific. Who needs Friday the 13th, when you've got the biosphere, and you actually look at lumps of matter walking around with legs on them, and you think about that for a moment, you realize just how odd that is to go from the Big Bang producing hydrogen and helium, and you go through the first generations of stars producing carbon, and then you have supernova explosions producing heavy elements. And the next thing you know, you've got lumps of matter with legs on walking around on beaches on planets. And it's an extraordinary thing. As I say, if you really think about it, almost strangely horrific, but fascinating at the same time. And so for me, linking that biological information, those observations, with what this all means in terms of the universe and how it came to be. What is this replicating, evolving matter we call life, and does it exist on other planets? And why does it even exist at all? Why would a universe give rise to pieces of matter that move around and eventually think about things? And there's no necessarily deep answer to that. I'm not suggesting there's necessarily a religious answer to that, but it's a fascinating question as to what has led to this material we call life. It's all just interesting to me, and any question that addresses that has always gripped my imagination.
I understand what you mean by possible horrificness of understanding these atoms, just keep gathering together in layman's terms and enabling something to actually walk and look either as cute as a Labrador or as terrifying as a T-Rex. But it's like as you were talking about, is basically, like I'm being 100% honest here, tears came to my eyes, because life is so amazing. Life is so magnificent. And we we scarcely ever think about this thing. I mean, how amazing is it that life somehow in some distant planet managed to conjugate itself in order for us, for example, the two of us having a conversation right now? The possibilities to me seem like, I don't know, impossible, basically. So it's a really, really fascinating topic.
And I think that realization is something that we should attempt to take a slightly more sociological turn of discussion here. I think it's something that it's scientific, but it should also be incorporated into the way in which everyone thinks about biology and life. Whatever sort of educational interest you do or do not have, I think we should all be educated to wonder at this thing called life, because I think as a species, we treat it with a casualness. We destroy other life, we destroy our own lives. No species that considers this extraordinary matter that has emerged in the universe would truly go around building nuclear weapons and planning to destroy cities or other representatives of this life, particularly its own representatives. I think if you can grasp the nature of biology, even at an atomic level, it sounds very reductionist. It sounds like something that would actually remove the emotion of life, thinking about lumps of matter walking around, as I said earlier, with legs on. You would think that might remove people's sense of wonder and reduce it to sort of cold atomic level. But in fact, I think quite the opposite. I think thinking about this wondrous process that has led to life actually makes you realize just how extraordinary it is, and how we should value all the representatives of this extraordinary matter on the Earth. The destruction of one species is a destruction of a particular form of this atomic arrangement that is astonishing, and it's terrible to destroy that just to build a house or something, or to burn down a forest to make way for some sugar plantation. You're destroying representatives of this matter that is the outcome of 3.5 billion years of universal development and ultimately biological evolution. I think if we could grasp that, maybe we would understand the wondrousness. So I think in some sense, taking a reductionist view of biology and looking at it at the atomic level can actually lead you to a much richer and deeper understanding of actually how wonderful this material is, and how we should care about it more and look after it, not least ourselves, but of course the rest of the representatives of this material we call life that happen to be on this planet with us.
Yeah, I mean, not just look at the geniusness behind it, everything that had to go within it in order to make it actually possible to happen, but also the beauty. I mean, looking at it from from the tree in and of itself to the various forms of trees. It really is a good piece of advice to look at it more reductantly, like from a reductionist point of view,
Yeah, so
because we'll understand how special this is.
Aesthetics.
Yes, please go ahead.
Yes, and as you say, there's the aesthetics of the actual organisms themselves. I think that's relatively easy to appreciate. You can look at a beautiful tree or some lion, and you can appreciate that. And the basis of that understanding of beauty is, of course, controversial. I think people like E.O. Wilson would say that it's some biophilia. It's a natural connection with the biosphere. That's certainly one level of appreciating life. But there's also the level of appreciating where that life form came from. Right down to the atomic structure and where that matter came from in terms of being produced from supernova remnants and stars. There are not many people that walk around and look at a lion and say, gosh, look at that wonderful piece of supernova waste. Isn't that amazing that it looks like that? And I'm not saying necessarily that people should go around thinking like that. I think that would be considered a little bit strange. I don't think people would go up to someone with a nice Labrador and say that's a wonderful combination of protons and electrons you've got in your pet there.
That would be good, good pickup line.
Maybe for a physicist, but I think that as I say, I think on a general level it would be quite strange to come out with that on a day-to-day basis. But I actually do genuinely think there's no reason why people should not have that appreciation as a general everyday thought. It's not that you have to express it in an everyday way, but I think to have a deeper understanding when you look out sometimes in a quiet moment, look out across a landscape and to actually contemplate where that life has come from, what it's made up of the atomic scale and the 13.6 billion years of the history of the universe. As I said earlier, that I wouldn't say the culmination of, because that strays into dangerous territory of suggesting there was direction, but the fact that life has come from extraordinary processes that have developed from stars to supernovae to the collection of that matter. I think everyone should have that appreciation. And I think now and again, people should consciously reflect on the atomic structure of life and the wondrous nature of an otter or a tree or even their pet Labrador and what atomically that represents. And I think if people did that, maybe they would wonder more, much more than even the aesthetics of a tree or a tiger, but wonder really deeply about the astonishing nature of this phenomenon of life and maybe value it more. And that's an educational step. It's partly science education, but it's also a step in the way in which we think about things and the way in which we value and consider the life around us.
I think that's a beautiful message for the end of our conversation, because the hour has passed already, and I just want to say, thank you very much for this conversation. Thank you very much, not just for the insights in terms of the scientific point of view, but also for this message at the end, which I believe, all things aside, will be the most beneficial for just about everyone. And thank you very much for that.
Thank you very much. It's a real pleasure to talk to you, and thank you for getting in contact. It's a pleasure to talk about these things generally, but I hope that anyone listening will perhaps develop some enthusiasm for biology, for science, for space exploration. But it's been a great pleasure to talk to you as well. So thank you for the time.
Thank you, and I hope that there will be sometimes in the future an opportunity to make perhaps a second episode.
Yeah, absolutely. We're very happy to do that.
Thank you, Professor. Thank you, and have a nice day.
Thank you.